let's consider constant volume heating of a perfect gas. So constant volume heating, and this is a perfect or ideal gas. And when it's constant volume, we refer to that as isochoric. So this is a change of state type of question. And so you would have your perfect gas in an initial state, or state 1, and then there would be a change to state 2. And the condition is isochoric, or that delta V is equal to 0, if you like. These are all, these scenarios here are all closed systems on a perfect gas. And so we would have N1, T1, P1, V1. It undergoes this heating, and so I'm going to put Q, excuse me, it's heating. So I know that Q is greater than, less than, or equal to 0. If it's heating, Q is going into the system, Q is greater than 0. Now whether I know these values or not, I'm just writing them in. Whoops, that would be 2, N2, T2, P2, and V2, and they may be the same, they may change, I may know them, I may not. Okay, and so what we have here is the ideal gas equation of state applies in each state. And so I can write that P1 V1 over N1 T1, that's what equals the universal gas constant R, and it's going to be the same whether I'm in the first state or the second state, P2 V2 over N2 T2. Then I look at what the condition is, and the condition is constant volume, and it's also closed. Because it's a closed system, my number of moles are not changing. Nothing's entering, nothing's leaving in terms of matter in the space. And because it's isochoric, I know the volume is constant. And so this reduces now to P1 over T1 is equal to P2 over T2. So from that, I know that any one of these can be an unknown, but I see that my second pressure is an operation on the first. So P2 is P1 equal to, or the other way around, P2 is equal to P1 T2 over T1. Okay, and then I can also rearrange, so just to insert the step, I'm crisscrossing here, P1 T2 is equal to P2 T1, and now I'm isolating like I did just there for P2, so P2 is equal to P1 T1 on the bottom of T2. I can also rearrange for temperature, and so T2 is equal to T1, again an operation on the initial value, on how it's changed. T2 is equal to T1, and then I've got a P2 over P1. So it's closed, so I know this. I have a formula for T2, I have a formula for P2, and I know that V2 is equal to V1 because it's constant volume. Excuse me. So I'm looking at the condition. So the condition was constant volume, or isochoric. The impact, of course, on that is that delta V is equal to 0. But what is the impact on the first law? So let's come down here and do that. The first law is, of course, that the sum of heat and work is the internal energy for these systems, that energy is conserved and can only change, the internal energy can only change by heating, cooling, compressing, expanding, right? So it's just Q and W, it's heat and work. And so du is equal to dq plus dw. You could also write that as delta U is equal to Q plus W, but I'm writing it this way. Does this have any impact on the first law, the fact that the change in volume is 0? If I don't have any change of volume here, I'm realizing that I'm writing outside of the view of the camera, my initial state of this gas, I have this volume, my final volume is the same. This is the same volume. And so, if it is indeed isochoric, then it has not expanded and it has not compressed, and there couldn't be, therefore, any work that has left the system or entered the system, respectively. So remember that dW is always equal to a minus P dV, and then I integrate it depending on whether it's reversible or not. Because dV is equal to 0, therefore dW is equal to 0. And therefore, the impact on the first law is that dQ, or du, is equal to dQ. Now I don't want to have a change in state property being equal to a path-dependent one, so I define that path. It's not just any dQ, it's the dQ at constant volume. Now remember that this dQ sub V is equal to something. dQ sub V is equal to what? Think about it. When heat enters a system or leaves a system, it will affect a temperature change. Just how much a temperature change depends on the heat capacity of the substance. And so this is equal to C dt. This is just, and it's constant volume, so I'll do this. This is a relationship, but it's not a formula yet to plug into. And of course, I would want to do this and integrate. And then that is constant, so I'm going to pull it outside. And so that means then that my Q sub V, which I just said is also equal to a delta U, is equal to a CV delta T. And I realize that I need an N. So this is in moles. My CV for a perfect gas I can write as 3/2 R. So so I can do that, or I can use the value that is given for the gas. So even when a gas is said to behave perfectly, you may get a value for the heat capacity. So don't be confused. Use that number. It'll be very close to this numerically, about 3 times 8 divided by 2. Okay, so this is a CV molar. Sometimes we see it written as a CV sub M, and that just means it's a molar CV, but it's 3/2 R. The units of R, this is going to be the 8.3145 joule per K mole, and my delta T, of course, is in Kelvin. And so moles goes out with moles, Kelvin out with Kelvin, and I'm left with a delta U, or a Q sub V, in energy units of joules. Perfect. Okay, so what do I have then for Q for this change? I have that Q sub V is equal to delta U, and that is equal to an N CV delta T. So I'm just showing you where it comes from, but when you do a few of these, you could just get right to it. The work, as we said, is equal to 0 because there's no change in volume. The delta U is equal to Q sub V, and we just did that. Delta H. Delta H is always equal to delta U plus the delta of the PV. And that's because H, thermodynamically definition, H is equal to U plus PV. So then I've just done the delta. Okay. And here, then, delta H is equal to delta U, and I just did that over there, plus, now I can do one of two things. I can substitute nRT for PV, and it's not isothermal, so that's going to do something. So then the only thing changing is the temperature, and so that would be nR delta T. Okay, so what I did was I substituted PV out and put nRT in, but the only thing changing is temperature, so there you go. Or, depending on what information you have, this could also be written as, again, it's constant volume, so it would be V times the change in pressure. It depends on what information you have. Now remember, if you are going to use this in liter and atmosphere, you'll need to convert your liter atmospheres to joules, and that's taking the ratio of the two R values. So that gives you 101.3 joules per liter atmosphere. That conversion factor simply comes from the ratio of the two values for R, which are always given on your data sheet. It would be 8.3145 joule per kmol divided by 0.08206 liter atmosphere per kmol. And so you see the ratio gets rid of the kmol, and you just have the number of joules per liter atmosphere emerge. The delta T, it's heating, so delta T is going to be greater than 0, and we know how to find the new temperature. And delta V is equal to 0 because it is isochoric. And in order to keep the volume the same and heat it, what do you think is going to happen to the pressure? It'll have to increase. So delta P, we know, is greater than 0, and we know how to find the P2 as an operation of the initial pressure times the ratio of temperature. So that's our first. And I'm just going to move that over just a wee bit, if I can, and get it all in view before I turn off the camera. So there you have it.